We will discuss Coulomb's law of electric force today. Charles Coulomb measured the force between charged objects using the torsion balance he invented. So the torsion balance has a suspension heat and a fiber. This fiber would turn an angle proportional to the force between object A and B, if there is any. So Coulomb can measure the angle of the turn of this fiber to find out what's the force between two charged objects. So to simplify, we will use point charge to represent those two objects carries electric charge. Coulomb found out the following property for two charges. The force between them is inversely proportional to the square of separation between the two charged particles, and is directed along the line joining those two objects. He also found that the force is proportional to the product of charge Q1 and Q2. He found out if those two charges are the same kind of charge, they repel. If they are different, then the force between them is attractive force. So put everything into an equation, we can find out the force between two charged particle Q1 and Q2 is force equals K, which is a constant. We call it Coulomb's constant, times Q1 times Q2 divided by R squared, where R is the distance between those two objects. The value of Ke in SI unit is 8.99 10 to the 9 Newton meter square per Coulomb square. The SI unit for charge is Coulomb. To honor the contribution of Coulomb to find out Coulomb's law of electric force. The Coulomb's law equation has exactly the same mathematical form as gravitational force we learned in Physics 1. Now, this is a funny picture, but actually what's even funnier is that Coulomb measured Coulomb's law first using the torsion balance he invented, as we said. And then we have Cavendish use the torsion balance invented by Coulomb to measure what would be the gravitational constant G in this equation. So actually, we have Cavendish copied Coulomb. Now, electric force is a force, right? So we have to recall what we learned in Physics 1. What about a force? What kind of quantity is a force? And then you can remind yourself that a force actually is a vector quantity. A vector quantity means it has magnitude, direction, and almost all physical quantity has a unit, which in other words, dimension. So we have to think about everything together. The Coulomb's law we represented in the equation, we write it in a magnitude form. So we don't write direction in the equation. Now in principle we could, but it just makes it a little bit more confusing. So let's keep it this simple. So the magnitude is given by K, Q1, Q2 divided by R squared. And how about direction? Direction, you just have to go back to the repulsive or attractive force between two charged particles. The force, the electric force, is always going to be along the line that joining those two objects. So if those two particles have like charges, then the force is directing away from the other charge. And the force from Q2 on Q1 and the force from Q1 on Q2, we can also go back to physics 1 we learned and recall what we learned about Newton's third law of motion. So there is action-reaction pair of force. Now this is a perfect example of action-reaction pair of force. The force from Q1 on Q2 and the force from Q2 on Q1, they are Newton's third law pair. And if they are Newton's third law action-reaction pair, then they have to have the same magnitude, opposite direction. So this is why they mutually repel each other away. Now this will also true if we have two negative charge. It will be repulsive force directing away from each other. Now, if they are different or unlike charges of Q1 and Q2, then the force is attractive. So the force from Q2 on Q1 pointing to Q2. The force from Q1 on Q2 pointing to Q1. Again, it's an action-reaction pair of force. So those two forces have the same magnitude, opposite direction. So the electric force is the second example of field force we learned. Gravity would be the first field force we learned. What do you mean by field force, you might ask me? A field force is a force exerted by one object on another object when they are not in contact. So they don't have to be in contact with each other to exert a force on the other one. Now think about gravity again. We have the Earth, the Moon, and we know the Earth is acting a gravitational force on the Moon, but we know the Earth and the Moon is separated by a very large distance. So field force is a non-distance force. The two objects doesn't have to be in contact. There are several similarities between electric force and the gravitational force, and of course there also are some important difference between electric force and the gravitational force. Now if you examine those two formulas, we'll find out both forces, the electric force and the gravitational force, both of them are inverse square laws, the force proportional to 1 over r squared. The mathematical form of both forces are exactly the same. If you replace those constants, you replace mass by charge. Now, the difference, gravitational force is always attractive. Electric forces can be either attractive or repulsive, depends on whether we have like sign charges or unlike sign charges. Now, because electric forces are vectors, right? So they have to satisfy the superposition principle. So if we have more than two charged particles, how do I calculate the electric force on one particle? So what I need to do is just to find the force from all other particles on that one particle, and then sum all the forces. Remember, this time you have to sum them as vectors. So vector sum of all the forces acting on the particle will give you the net force on that particle. To make it more concrete, so we have charge Q1, Q2, Q3. I want to find out what is net force. So in other words, is total force on charge Q3. What I need to do, first, I find out the force from Q1 on Q3. Q1 and Q3 are both positive, so the force is repulsive. So the force from Q1 on Q3 directing away from Q1 along this line. And then we have the force from Q2 on Q3. Q2 is negative, Q3 is positive, so the force between them is attractive. So the force from Q2 on Q3 is pointing into Q2. So this is my Q13, which is the force from Q1 on Q3. F23, the force from Q2 on Q3. So those are the two forces acting on Q3. What I need to do, I need to add F23 and F13 as a vector. That would give me the net force acting on Q3.